Well, sorry for the interruption. I may have had too much data in my phone. I deleted a few half-hour long videos. Hopefully that will prevent the phone from triggering a shutdown. I was talking about partial pressures, where the pressure contributed by a gas is equivalent to its mole fraction. So another way of stating that is that the total pressure is equal to the mole fraction of each one of the contributing parts. Oh, right, you gotta put P total here. So take the total pressure, multiply the mole fraction of each by the total pressure, and they will add up to the total pressure. Okay, so the seventh concept, this was actually a continuation of the sixth concept. The seventh concept was, no, it was that, sorry. And then 8 was the energy of the gas molecule is related to 1/2 its mass times its root mean square velocity. What is the root mean square? It is the velocity of the molecule of the gas in a sample of gas that has the average kinetic energy. Root mean square is a little bit higher than the average velocity because the average kinetic energy is a little bit higher than the middle point of the bell curve distribution of molecules, because kinetic energy is related to the velocity, the mass times the velocity squared. So if a molecule has a higher velocity, that has a high effect, the squaring of the velocity has a high effect on the kinetic energy. So the average kinetic energy of a collection of gas molecules is a little bit higher than the middle of the bell curve distribution of the velocities of the molecules. The one thing I want you to remember from all this is that all samples of gas have the same kinetic energy as long as they have the same temperature. Does that mean they have the same velocity? No, because if you take a sample of helium gas at 25 degrees Celsius and a sample of nitrogen gas at 25 degrees Celsius, they'll have the same kinetic energy because they're both at 25 degrees Celsius. But if you look at one molecule of each one of those gases, even though the two molecules say they might even be going, they might have the same kinetic energy. Two molecules of different weights can have the same kinetic energy, but the lighter molecule is going to be moving faster. Just like two bullets can have the same kinetic energy, but if they're different weights, then the lighter bullet has to be moving more quickly to have the same kinetic energy as the heavier bullet. So the molecules always have a sort of bell curve distribution of velocity. As the temperature gets hotter and hotter, that bell curve tends to widen. So you get a wider range of velocity as the gases get hotter. One of the formulas that came about as a result of a study of the kinetic molecular theory was that the root mean square velocity of a gas is directly related to its molar mass. So molar mass is m, r is the gas constant, T is the absolute temperature. So if you take the square root of 3 times the gas constant times the absolute temperature divided by molar mass, you get the root mean square velocity of the gas. And this allows scientists to draw a proportionality between the rate of effusion between two gases. It is directly related to the mass of the molecule, but in a inverse manner. So the lighter gas will work its way through a pinhole faster than a heavier gas. And so if you have perfume molecules, for instance, you'll be able to smell a lighter perfume more quickly than you will a heavier perfume. You'll eventually smell both, but the lighter perfume has a higher velocity and will diffuse more quickly as a result. Finally, the 10th point is that gases deviate from ideal behavior, and this is underlined by van der Waals equation. And van der Waal realized that the assumptions of the ideal gas law were not 100% correct. First of all, gases do have a finite volume. They're very small, but they do have a certain amount of volume. And the other idea was that they do actually interact with each other. They do kind of, the molecules do have some stickiness to each other. So gases deviate from ideal behavior. And this is the formula. P is equal to nRT over V minus NB. This part here is the acknowledgement of gases do have volume. And the next part is that the pressure is reduced by the fact that gases are attracted to each other. So this term recognizes attraction between molecules. And A and B are different for each gas. Each gas has its own value, A and B. So when you're doing van der Waals calculations of pressure, you have to look up the values of A and B and incorporate them into the equation to get the actual pressure that would result for the gas. And then you can compare it to the ideal gas equation and see how much it deviates. Let's do a couple practice problems just for the sake of reminding you of what we learned in that chapter. The first one I'd like to do is 1018, and I just realized I didn't set my book aside, so I can find it quickly. Chapter 10, here it is. So the question is here is just basically making conversions between different pressures. So let's show you how that works. So if you have a pressure of 0.85 atmospheres and you want to convert it to torr, you would say there's 760 torr per 1 atmosphere. You can basically make a conversion factor out of any two of those conversions I showed you. I'll show you a big long list. 1 atmosphere equals 760 torr equals 760 millimeters Hg, etc., etc. Pick any two and you can make a conversion factor. So obviously pick the two that are going to help you to eliminate whatever it is you're trying to eliminate. Here you're trying to get rid of atmospheres, so I put atmospheres on the denominator, and I wanted to convert it to torr, so I put torr in the numerator. 760 torr equals 1 atmosphere, so the answer you get is 646 torr. B, that was A. B asks you to convert 785 torr into kilopascals. There's 101.325 kilopascals per 760 torr. So torr cancels now, and what you get is, after sig figs, 105 kilopascals. C, 655 millimeters Hg times 1 atmosphere per 760 millimeters Hg allows you to cancel millimeters Hg. Millimeters Hg is what they use on a blood pressure cuff. When they measure your blood pressure and they say 120/80, those numbers are in millimeters Hg. Or you can also say torr because they're interchangeable. So what you get is, let's just see, 0.862 atmospheres. After sig figs, you're only allowed 3. D, you have 1.323 times 10 to the power of 5 pascals, and you want to convert it into atmospheres. There's 1 atmosphere for every 101,325 pascals. Pascals cancel, and you get an answer of 1.31 atmospheres after sig figs. The last one is E. Let's just erase that over here. 2.5 atmospheres times 1.01325 bar per 1 atmosphere allows you to cancel atmospheres, and what you get is 2.53 bar. The second question I wanted to do with you was number 24 and 24. P1V1 is equal to P2V2. And, well, let's read you the question.
A fixed quantity of gas at 23 degrees Celsius exhibits a pressure of 735 torr and occupies a volume of 5.22 liters. A. Use Boyle's law to calculate the volume of gas will occupy if the temperature is increased to 1.88 atmospheres while the temperature is held constant. B. Use Charles's law to calculate the volume of gas will occupy if the temperature is increased to 165 Celsius while the pressure is held constant. Very well.
So we're going to use P1V1 equals P2V2, that's Boyle's law. You start off with 735 torr. Now it doesn't matter which units you use as long as you're consistent across. 5.22 liters is equal to 1.88 times, I guess that was atmospheres. Let me just double check because I didn't write it. Yep, 1.88 atmospheres times 760 torr. See, we have to use torr, so I'm converting to torr per 1 atmosphere, so that allows me to cancel atmospheres. And then we're going to multiply, well, we're going to find out what V2 is. That's the one thing we don't know. And what we get is that V2 equals 2.68526, which rounds down to, rounds up to 2.69 liters. That's the volume before and after. Okay. Then part B, use Charles' law, which is V1 over T1 is equal to V2 over T2. You don't have to memorize which law it's called. Just remember the ideal combined gas law. P1V1 over N1 T1 equals P2V2 over N2 T2. And you'll notice that you just cancel out the parts you don't need and you get whatever law you want. You get Boyle's law or Charles' law just by canceling the parts you don't need. So just memorize that one ideal combined gas law, and then when they give you the problem, the things that stay the same, you just cancel out because it's the same number on both sides. So why would you even include it in the calculation? It doesn't affect the outcome. So what we don't know here is V2. We know everything else. Obviously, if you have 4 variables, you have to know 3 of them. They have to give you 3 of them, or you have to have the means to find 3 out of the 4, and then you can find the 4th one. So we have 5.22 liters over 23 plus 273.15. Remember, you got to convert to the absolute temperature scale in Kelvin to do these calculations properly. 273.15, and so V2 comes out to 7.72 liters as your final answer. Now, I would like you to try, and I know you don't have the chapter, so I'm going to show you the questions I would like you to try. They are questions, nice if I kept it open, 33 and 41, and I'll review them with you tomorrow. And then right after that, I will show you some review questions that you can do for the overnight, and then we'll review them as a kind of mock test, and then I'll proceed to the organic chemistry chapter, and then we should have a test by Friday, and that's the last test you're going to have. So let me show you the 2 questions I'd like you to look at for homework. So they are 33 and 41. Is that what it is? Yeah, so 33 is this one. The Hindenburg was a hydrogen-filled dirigible that exploded in 1937. If the Hindenburg held at 2.0 times 10 to the 5 meters cubed of hydrogen gas at 23 degrees Celsius and 1 atmosphere, what mass of hydrogen was present? And the next question is 41, which appears here. In an experiment reported in the scientific literature, male cockroaches were made to run at different speeds on a miniature treadmill while their oxygen consumption was measured. In 1 hour, the average cockroach running at 0.08 kilometers per hour consumed 0.8 milliliters of oxygen at 1 atmosphere pressure and 24 degrees Celsius per gram of insect weight. A. How many moles oxygen would be consumed in 1 hour by a 5.2 gram cockroach moving at this speed? B. This same cockroach is caught by a child and placed in a 1-quart fruit jar with a tight lid.
Assuming the same level of continuous activity as in the research, will the cockroach consume more than 20% of the available O2 in a 48-hour period? Remember that air is 21 mole % oxygen. I will give you the answer tomorrow.